Thank you. Thanks a lot for the introduction. Of course, very happy of being here. Very thankful for the organization and for IMPA for this possibility of, being in these wonderful conferences, meeting old friends, meeting new ones, so many young people. Okay, so as announced, I will talk about equidistribution. So this is subject from Maracal of geometry. So my setting is X, will be X, a projective variety. Over the field of rationals. Indeed, I can take any number field, but I will stick in this talk to this setting of dimension D, at least one. Okay, so I will consider on it a height function. Okay, height has appeared many times in this conference, luckily. So this is the central actor of my talk somehow. So this will be a function on the set of algebraic points of X with real values. Okay. So this is about the question is about the analytic distribution of Galois orbits of points, okay, subject to some arithmetic conditions. Okay. So this is what we will see eventually, that some very soft algebraic genericity plus some arithmetic condition will, in some situations, induce a very, very specific analytic distribution for these Galois orbits. Okay. So the central result in this field is the equidistribution theorem of Young, 2008, which is well, it's a development after many other people, but especially initiated by Spiro, Ullmann, Sang in 1997. Okay. This is quite an important result that had many applications in Diophantine geometry, in particular to the was indeed central tool for the Bogomolov conjecture for the proof, and then for Mordell conjecture, counting on rational points in curves of genus greater or equal than 2. So this is what I'm going to. Well, I'm not going to talk about this application at all, but about this tool. Okay, so to illustrate, if I don't know if maybe some of you have never heard about this before, never seen it before. Indeed, it is something that sometimes can be seen, can be visualized. So this is what I want to show with a small experiment. So the thing is, for instance, I've talked about. Sorry, yeah, thanks. Maybe I have to share something. Where is this? Okay. So simple situation, that is, have a sequence of univariate polynomials with integer coefficients that will have increasing degrees. That will be my soft algebraic condition. They will be irreducible because I want to study Galois orbits. Okay. So I will consider their roots. And the arithmetic condition is that will impose is having small coefficients, bounded coefficients. Okay. So this is the experiment. That is, I am giving. Well, I have borrowed this script from Roberto, who has indeed a very nice survey about these things. So let me explain what we are doing. So this is where I want to stop. Indeed, I will produce a random polynomial. A polynomial of the shape of degree, the degree of the polynomial Fn would be n, okay? And then I will have the coefficients of Fn that will be either 0 or plus or minus 1, very small. Okay. What happened with the zeros of this? I mean, does any one of you know what happened with the zeros? It's very classical. No? Okay, I mean, there are. The question is, I'm taking a sequence. Okay, I will let n increasing 1, 2, 3, etc. Okay, and for each n, I will take a polynomial fn with integral coefficients. The coefficients will be very small, either 0 plus or minus 1. Okay, the degrees will be very high. I will also request them to be irreducible. Okay, and I wonder where are the zeros of this polynomial? Where are the solutions of the equation fn equal to 0? Okay, so for instance, this is something that a very basic property. They are bounded. Okay, indeed, it can be shown that they are in the square of size, well, of radius, say 2. Okay, they are always there. Okay, this is something. There is some localization. We can say something about the location of these zeros. Okay, but indeed, more can be seen, especially when you go to higher degrees. This is so. For instance, here I'm taking. This script is producing a different polynomial each time. So, sorry, it has to be executed. Okay, that's it. So here I have a polynomial of degree 4. Well, this is not very visible because it's a polynomial that has roots well, in the real and imaginary axis. Let me repeat it to see if we see something else. Oops. That's it. Here we see 4 roots. Okay. Of course, they are inside this square. Okay, and they are symmetric with respect to the real axis. Nothing more can be really said. Let me go to higher degrees, so degree 10. Okay, so we have these 10 roots still symmetric through the real axis. Of course, maybe something can already be seen. Let me repeat it. Different picture. Maybe still another. Okay, I mean, they look a little bit like they're doing like a ball. No? But okay, I can go to higher degrees as promised. Let me put, I don't know, 30. Okay, so maybe here we're already seeing something, okay? So still they are in the square, but they start to take a special configuration in the space, okay? They look as if they were converging to the circle. I can repeat, it's a random polynomial, I can repeat it to see. Okay, same situation. Of course, there are some, I mean, it is not perfect. It is more like a statistical statement. Some roots might be, one isolated root or two might be a little bit farther away, but in general, they are converging to something. So here, I think what I can do is to make this plotting like progressive in degree 10, 50, 100, 200 to see what it gets. So here is the evolution somehow of this problem. No? This is degree, I think, 50, 100, degree 200. And there it is. I think it is really, really clear. So this is the phenomenon we want to study. We want to give some arithmetic condition that somehow forces some special distribution. This time is the uniform measure in the circle, but it can be anything else. Yeah. This is a deterministic process, what I am going to explain. It's not probabilistic. I'm taking it random just to show, but the theorem says the theorems we are going to see are not indeed for random polynomials. They are for polynomials satisfying some arithmetic condition. Then the distribution will be always to this limit. Okay. Okay. That's it. Okay. So the explanation of this is the so-called Bilu's equidistribution theorem. which was done right after Spiro Ulmo-Sang and inspired by that for the projective space, for the projective line, indeed. Okay. So if I take, says the following thing, if I take a sequence of algebraic points in P1, okay, with degrees increasing, I mean the, say, limit, well, this going to infinity, and height going to 0, okay, where here I put the veil height, the most simple height, the first one explained by Farbod. Then the Galois orbits of these points, here I will put infinity because I'm considering the Archimedean Galois orbit, will converge to a measure that we'll call eta of S1. This is the uniform measure on the circle. This is the theorem. Okay, so why this theorem refers to that situation? This is because in my situation I will take xn will be a root of this polynomial fn, such a way that all the other roots are the Galois orbit of this one. And I will have that, of course, the degree of xn will be n, and the veil height of xn is going to be the sum, well, 1 over n, indeed, 1 over then the sum over the Galois orbit of the function log plus of absolute value of y. Here this is the complex absolute value, okay, which can be written as the Mahler measure. This quantity can be written as the Mahler measure. Well, this is 1 over n, the integral over this circle of logarithm of absolute value of the polynomial fn with respect to this measure, okay? And this, I don't want to go to cross this line. This, because it is a polynomial with small coefficients, can be bounded by log of n plus 1 over n, which of course is going to 0 as requested. Okay, so this is, in this situation, we have a sequence of points with a height conversion to 0, okay, and increasing degrees. Okay, so now I want to go to the more general situation. No? So I will explain this phenomenon in a general setting. So this will be what's sometimes referred to arithmetic equidistribution. Okay, so I will introduce the different actors. This is, I mean, I will try to give intuition about that, but of course I will not be able to give all the precise definition. I hope it will be understandable enough. In any case, I will consider X, my variety as before, and a device called an adelic. Let's call an adelic R divisor. Okay. An adelic R divisor, the space of them is called div x r hat. Okay. It's a pair composed of a Cartier divisor and a family of Green functions. It's a family of Green functions. Each of a Green function for me will be a function defined on the for each v, for each place of the field of rationals. I will take I consider the analytification. The function will be defined in the complement of the support of the divisor with real values. that will be continuous and have some specific asymptotics at infinity that is close to the support of the divisor. On the other hand, I will not assume that it is semi-positive, as was in the lecture of Farbod. I will not assume it is plurisubharmonic in general, okay, although that will play an important role. So this data, I mean, for those who have heard about this before, this is equivalent to well, when D is a divisor, and not an R divisor, sorry. This is a Cartier R divisor. And by the way, I have to add here that the variety is normal to work with R divisors. So when this is a divisor, this is the same thing as considering the associated line bundle with a matrix, okay? And plus the canonical section, of course, and the relation is that the green function is going to be equal to minus the logarithm of the norm of the section. Okay? So this is, I mean, there are these 2 points of view, as in algebraic geometry, divisors and line bundle, and this is the link in this metric situation. Okay, so for instance, okay, if you take x equal to P1, okay, and you take D, the divisor at infinity, and you take green functions for Z, no? Z is the affine coordinate. The affine coordinate of P1, as usual. The green function, if I take it as the log plus of Z, V, this is admissible, and this will give me the base height. So I will be interested in small heights. Let me make some place here. I mean, small height means the small values of the height function. So there are several invariants associated to heights. The basic ones is the absolute minimum. So I will denote mu abs of d bar. This is called the absolute minimum. Okay. This is the infimum over all sequences of points, algebraic points, of the height. Sorry, I skipped a definition. Let me forget about this. Well, let me write this. Let me write this, and then I will come back to the definition. I have skipped the definition of the height. So associated to an adelic R divisor, one can define a height function. Okay, so this object, this arithmetic geometric object, is the input that defines a height function. So once you define this height function, which is well, I will put it here indeed. It's as before. It's what I have written before indeed. Okay. Mm-hmm. And just to be a little bit more complete, let me give the precise definition. If you take x a point, let me take it outside the support. Okay. Though this is no restriction, because if I want to consider points in the support, I shall have to take a linearly equivalent divisor. Then the height is defined as an adelic sum of and in each of the terms, I have to consider an average over the Galois orbit, the Viadic Galois orbit. So I will take this is the Viadic Galois orbit, that is the image of the algebraic Galois orbit inside the corresponding analytic space. Okay. This is the average of the green function. Here it is where green functions appear, and I am taking the average. So here I will put the cardinality of that dyadic orbit. And there is no, yeah, this is for XL. Okay, this is the definition of the height in the most general context I am considering. So I will say a few words about that some minutes. But in any case, this is a function with real values. So from this space, and this function is something which is not continuous at all. I mean, it is this is a discrete object, the set of algebraic points. So, but I will consider the minimum of this function. It is the infimum of the inferior limit of this height over all sequences. This is one quantity, but that will be more important is the so-called essential minimum, which is the same thing. But when you take sequences that are generic, which means that algebraically they converge to the generic point of the algebraic variety, or in other words, they are not repeating or staying in any proper subvariety an infinite number of times. Okay, this is called the essential minimum. So you can. One can think of how one should think about these notions to have the correct intuition. In my view, is the height. I mean, this has many interpretations. Okay, it's really many different phases. But from the point of view of Diophantine geometry and computer algebra too, you want to understand this as a notion of complexity, of arithmetic complexity or bit complexity, if you want. So this is like a bit complexity for points over Q bar. Okay, very similar to the notion of to the choice of a norm in a lattice. Okay, so if you have a lattice, like a Zn, you want to consider norms, and when you have norms, you can work with that and prove finiteness statement and counting and so on. So this is the same thing you can do with heights. Okay? In particular, when you state not with, when you restrict to a number field or to bounded degree points, you have finiteness statements like Northcott. Okay? But in general, we want to consider algebraic points. Okay? So this notion of complexity is defined coherently for all these algebraic points. But this is very good, but this has a price. The price is that you lose this finiteness condition. So if you go to very small values, you say I want to look at points with height smaller than that quantity. Okay, sometimes you get a finite number of solutions. Okay, but as soon as you increase, there will be like a threshold above which you find many points. For instance, you find generic subset of points with that height. There is a sort of like a phase transition in this situation. And this phase transition point is codified by this quantity, this essential minimum. So to give you an example, a concrete example, maybe at the price of, I don't know, not finishing my talk, but okay. Let me consider, for instance, on P1, for a point in P1, I can define the height of this point h, x being x0, x1, as the height the Veil height of this same point plus the Veil height of this same point, but with the coordinates x1 minus x0 in the second. Okay? This is essentially the pullback of the height of some line in P1 times P1 with the canonical metric of that variety. So this is the so-called Sangsagier height. It's very simple example. Here you will see that if you look at the values of the height function, these are the reals, this is the 0. This height is non-negative, because in general heights can be negative. This is non-negative, and this 0 is the absolute minimum. Okay. But there are very few points. There are like 6 points which realizes this value. Then you have some numbers that, some other values that appear. And there is some critical point here that is the essential minimum. The essential minimum, after which you cannot get finiteness. Okay? And this number is known to be between 0.24 and 0.254, something like that. This was proved by Zagier, and this by Hodge. Okay? And after this, you have a dense subset of height values. Okay? By the way, this is part of an ongoing work with Jose Burgos and Ricardo Menares in Chile. It's extremely difficult to compute in practice, okay? But nevertheless, we know that these values exist, and I want to somehow highlight the role they have in equidistribution. So in any case, after this point, in this particular example, but this is a general picture, after this point, we are in the case of a curve, so we're talking generic sets are infinite sets. After this point, there are infinite algebraic points with heights approaching this thing, okay? And so the idea is that, okay, there are infinite numbers of points, but below that there is nothing. They have somehow very small room to move, okay? And this is somehow which promotes or indicates that there might be some rigidity happening. Okay, so for instance, from now on, I'm going to describe the equidistribution theorem. This is my goal now. I will assume that D is big. Okay. This big is that it has enough sections, enough global sections. This will imply, for instance, this is like the minimal assumptions you need geometrically to have equidistribution. This will imply that this essential minimum is indeed finite. I mean, it is not minus infinity. Okay, you need which can happen, for instance, in an anti-ample case. We'll assume that. This, by the way, this is the fact that the ball, of course, the ball of D is greater than 0. Okay, so the thing is that heights and equidistribution are very much related to positivity, both geometric and arithmetic positivity. So I will consider shift. First of all, I have to consider shift. Well, let me say something before, just to motivate you. If you have that D bar is big now, note the difference, note the bar here. Here there is no bar. Arithmetically big means that the arithmetic global sections, there are many arithmetic global sections. This is coded in the fact that the so-called arithmetic volume is strictly positive. The global sections in the arithmetic sense are global sections. In the geometric, that moreover satisfy some inequality for their norm. The supremum of the norm evaluated on those sections is at most 1. Okay. This is the arithmetic analog. all this business is about, all this kind of business is about looking at appropriate parts of algebraic geometry to pick what you want to prove, to extend to produce some arithmetic analog, and then use that as a tool to solve some problem in number theory. So if this is big, then for instance, you have that the essential minimum of d bar is strictly positive. This is, I am not proving that, but this follows very, very directly from the definitions. Okay? So I will consider shifts. I will consider shift that I will need technically. For any real number, I will shift my adelic R divisor by keeping the same geometric divisor, and then for the green function at infinity, I take a minus t. I shift it by t. I download, then I make it smaller with this t, and all the other ones are keep the same. And I am just shifting this arithmetic part, arithmetic contribution. So this is necessary for this appears in an important theorem of François Balai, which characterizes the essential minimum in positivity terms, and says that this quantity is the supremum over of t such that d bar t is big. So this means that one can read or relate this numerical quantity to the bigness of this arithmetic divisor. No? In any case, to how much you can take to this arithmetic divisor, or put, if you put 10 negative, and still keep it arithmetically big. Indeed, this is again, has a geometric basis. This follows from a result of I, which is the arithmetic theorem of Buxom, Desmailly, Paun, and Peternel on the duality between the pseudo-effective cone and the cone of movable curves, which was proved. The arithmetic version is of I. Okay, so after this I will need some definitions. I will suppose now, but just for the moment, that d bar is big. This is just for this definition. Let me put definition here. Arithmetically big. It will be always geometrically big, but in general not arithmetically. But if it is, I will define the notion that a pair phi, or say p bar in any case, is a Neff approximation of d bar. That is, I will be considering other R divisors that will approach my d bar. What does this mean? This means several things. First of all, who is p? I will have some birational modification, and p is indeed p bar, is an element in this modification. It's an adelic R divisor in this modification. Okay? And I want that p bar to be Neff. Neff means is semi-positive. Now, semi-positive is that condition that the green functions are plurisubharmonic. And numerically positive, not negative, right? The height, the associated height is always non-negative. This is the fact of being arithmetically Neff. Why? Because the height of points that I am describing is the arithmetic analog, as Farbod explained, is the arithmetic analog of the degree of curves. Okay, and this is why this is the correct notion of netness. I want this, and I want that the pullback of d bar minus this p bar is pseudo-effective. Okay. These are the approximation. So this kind of divisors, these are related to Zariski decomposition, or arithmetic Zariski decomposition. Well, Zariski decomposition, well, one of the standard definition is that is an R divisor of these shapes whose arithmetic volume is equal to the arithmetic volume of my d bar. Okay, so it is a statement that is sought, that is wanted because it's a way of reducing an arbitrary adelic R divisor to a positive one, which has better properties, of course. Unfortunately, unluckily, this is false. I mean, this does not exist in general in dimension greater than 2. In dimension 1, it is proven by Moriwaki, but in greater dimension does not exist. But there is a replacement that is called the arithmetic Fujita approximation. That is, it's an approximate version of this for every epsilon. You ask for an adelic R divisor like this, whose arithmetic volume is greater or equal than the volume of d bar minus epsilon. And this does exist. I mean, you can approach with positive adelic R divisor the volume of d bar up to any desired precision. This was proven by Chen. It's the theorem of Chen. Yeah. They used that in the second proof of that. The initial proof was, I mean, the first proof was more constructed with blow-ups along the locus of small sections and so on. But then there is a much easier proof with the arithmetic Newton-Nagunko bodies. Exactly. As it is done, I think, in the geometric case, right? I mean, the Fujita, geometric Fujita approximation can also be proved with Okungo bodies. Okay. So I will not be considering the arithmetic volume for this. For this approximand, I will be considering others invariants. The first is the so-called, I will note it rho of d bar. I will call it in radius for reasons that we will see later, or not, depending on time. That it is the supremum over all this p bar. I am skipping the birational modification from the notation. I mean, this is like I understood it exists, but I am not writing that. Overall, this approximation of quantity that I will call R of P with respect to D, but this quantity is also called sometimes the geometric in radius or the pseudo-effective threshold, which is a measure of how big is this approximation with respect to a fixed one. That will be this D. This will be fixed in my application. Okay. And then there is another object that is defined. I will not explain how, but for every place, it is possible to define a measure that I will call omega d bar v. This is the so-called, well, so-called by me, Chen measure. I mean, it was defined by Chen, and I think it is sufficiently important to deserve a name, which is a measure on the analytic space, of course. Okay. and that has, well, it is a limit, can be understood as a limit of Monge-Ampere measure, the C1 of the approximations. These are the so-called Monge-Ampere measures that were also very rapidly mentioned by Farbod. Okay. This is a measure which has a mass. The total mass is the volume of the algebra of small sections. This R(d bar) is the algebra of small sections. This volume is the, gives you, this geometric volumes gives the mass. Okay. Okay, so finally I can state the equidistribution theorem. This is the theorem I want to publicize, which was done, well, we did with Francois recently. Okay, so this is what I'm going to write is an extension of the equidistribution theorem of Yuan. Of course, I am not pretending this is more important than that. This will contain it and has a very clear purpose. But historically, that theorem is the important one, and of course the predecessor by Spiro-Ulmo-Sang on abelian varieties and Bilu and so on. This is a general statement that is trying to contain, I mean, to generalize that, but also to contain other cases, other important cases that were outside the scope of that theorem. So there is a condition. I will have to assume that the limit when t goes to mu, where mu is short for the essential minimum, of the quotient of mu minus t of that in radius of the shift as t goes to the essential minimum is 0. Okay, this is a condition that says that as t approaches this adelic divisor is still big, but every time is less big. Okay, so this in radius is decreasing. I want this to decrease, but not very fast. It has to decrease less than the discrepancy between t and the limit. Then there are two conclusions. Then, for every v, for every place, you have first that the limit of associated chain measures normalized by their mass converges. And then I will call, well, this is the first statement, convergence of measures. I will call mu d bar v the limit, call the limit like this, okay? And second statement is that this limit is the equidistribution measure. That is, for every sequence XL of algebraic points, which is generic, and the limit of heights is the essential minimum, we have that the Galois orbits in the corresponding analytic space are converging to this measure in the sense of measure, as usual, as in the experiment. This is the thing. Okay. So how much time do I have? Do I have some time?
Yeah, 5 minutes.
Okay. Okay. Okay, so this result. Okay, looks probably quite scary after all these definitions. I apologize. So the particular case of your theorem is the case when the essential minimum coincides with the absolute minimum. Okay? So in this case, the condition is okay. It's always verified, and the limit measure is given by the Monge-Ampere measure of d bar. This is also I have also to assume that d bar is semi-positive. This is C1 of d bar v over its mass, which is the intersection. This intersection number. Okay. So how is the story? I wanted to explain finally, mostly explaining this result and the background, but the story was that this theorem, and also Yuan in some situations, is difficult to apply because this implies, for instance, the computation of this invariant. And furthermore, to apply this one, you have to compute this Neff approximants. Okay? This is, in practice, is extremely difficult. No? For instance, we are fighting with this small example with Jose and Ricardo for a long time. And we still don't know. For instance, we still don't know if in that particular example there is an equidistribution phenomenon or not, because there is a condition to verify here. So the thing is that we examined this phenomenon in the Toric situation, no? That is for Toric varieties. Okay, so this was done by Burgos, Philippon, Rivera-Letelier, and myself some time ago. Okay, so the thing is that in Toric varieties, I mean, this is the combinatorial part of the story. I'm probably not going to tell a lot now. But it's, which is nice is that everything we have seen so far can be computed, can be put in explicit terms. Just to, I don't have the time to give all the definitions, but I will nevertheless make a picture so you can see what you get. So let me consider X a Toric variety. A Toric variety for some torus, and d bar a Toric adelic R divisor on X. Okay, so to this data one can associate first a polytope in the vector space associated to the character lattice. Okay. And then you can associate for each v, for each place v, a function, a concave function on that polytope called the v-adic or local roof function. Okay. So, and then find, well, you have that they are concave and continuous. And moreover, they are equal to 0 for all but a finite number of places. There are only, in each example, there is only a finite number of places that is counting. So you can consider the sum of them. This is called the global roof function. It's big. D is big, thank you. Yeah. Which is the thing that ensures that this is d-dimensional, right? The bigness is the same thing as saying that this is actually has dimension d. Okay, so my picture. This will be the last. probably the last thing, or almost. So this is my polytope. Here I am depicting the case for easiness. I will depict the dimension 1 case. Okay, so this is my polytope. I have a bunch of local group functions. For instance, I have one which is something like this. This would be my first group function. Then I have another. That's great. So many colors. It's fantastic. Say something like this. And then all the rest are 0. I'm just supposing that in my situation there are only 2 non-trivial ones. So the global root function is the sum of them. Well, I don't know if I can, and I can do this properly, but I will try something like this. Maybe. Something like this, okay? This is the global, and these are the local, okay? So the thing is that from this picture you can read everything. I have explained it so far, okay? So first of all, the bigness of the divisor, okay? This is seen in the fact that this is of dimension 1, okay? Then the essential minimum, in this case, is computed. It's the top of the global root function. This is the essential minimum. The absolute minimum is the minimum of this global root function. I'm sorry, I cannot write everything, but well, it's the minimum. In this case, it's exactly the 0, just by chance, somehow. Okay? So you see, for instance, that the Yuan condition, the condition that appears here, the Toric case is extremely restrictive because it imposes that the maximum and the minimum of the root function are the same. It's the same as saying that this function is constant. It's a very, very particular case. It's essentially the canonical case, which was very well understood, for instance, since Bilu theorem. Okay, so this is one thing. So we're considering this general case. Then the thing is that for a t approaching the essential minimum, I had to cut this picture, right, and keep the subset that appears here. In this case, is a polytope. Okay, if I am in dimension d equal to 2, I will have a base polytope something like this. But then inside here, this is st, because it's I call it st is the sublevel set of the function, the set where the function takes values at least t. In general, it is a convex body. Okay, so what I need is that this convex body is not small enough in terms of the width, or equivalently, by convex analysis, in terms of the in radius. This is why, I mean, this geometric quantity, the pseudo-effective threshold, indeed can be interpreted in the Toric case as the in radius of the corresponding polytope. This was remarked by Tessier many years ago, and well, led him conjecture several inequalities for divisors. So it is the width that is counting here. This is the rule is essentially that. So you want that this width is large compared to the discrepancy here. Okay. So if this is the case, there will be equidistribution. Okay. So if you have something like this, like a sugar loaf, essentially, someone suggested, the sugar loaf, there is equidistribution, right? Because the top is smooth, and in general you have this width, which is quite wide indeed. Okay. On the other hand, if you have an alpine house, probably you don't have many in Rio. In these cases, there is no equidistribution because the width is proportional to this discrepancy here. Okay, and once you have that equidistribution, which are the measures? And this is why I made the other picture. They depend on these local functions. Essentially, you have to take, well, you have that in this point, which maximizes. This is the maximizer point. I have, of course, a subgradient, which is 0, because it's a maximizer. That is a linear a linear map or affine map that lies exactly above the graph. Okay? So this will be the contribution of subgradients of the local root functions at the same point, because this one is the sum of the other two. This, let me call it U1, U2. So we can prove in general, this we did in that previous work, that there is a unique family of balanced, what are called balanced subgradients. Let's call UV. That is, each UV is a subgradient for the corresponding local root functions, and they are balanced. They sum up to 0. Okay. Well, I will finish more or less here, but these subgradients will define the measures, the equidistribution measure for each local, for each place. Okay. So so the story was that we found a version of this statement before. Okay. So this was the guide that we used to generalize Yuan equidistribution theorem. Now this much more general theorem can be applied to other situations, and it's being done. Okay. And this, on the other hand, they allow us to understand better this Toric situation. So, okay. I think I will stop here. Thanks for your patience.